Today we are going to discuss the lecture number 9 on symmetry and group theory. In this lecture we will discuss about the applications of symmetry and group theory. Applications like the chirality, polarizability and the orbitals used in the molecular orbitals and the hybridization. Applications of group theory. First application is predicting polarity of molecules. A molecule cannot have a permanent dipole moment if it A. Center of inversion, B. belongs to any of the d point groups, C. belongs to the cubic groups, that is tetrahedral or octahedral. This means that molecules belonging to Cn, CnV, Cs may be polar. Second application is predicting chirality of molecules. Chiral molecules lack first an improper axis of rotation, that is Sn, second a center of symmetry I, third mirror plane sigma. D2H and tetrahedral contains I, C3H contains sigma H, tetrahedral contains S4. Therefore, molecules belonging to these point groups cannot be chiral. Third, predicting the orbitals used in molecular orbitals. Molecular orbitals result from the combining or overlapping of atomic orbitals and they encompass the entire molecule. Fourth, predicting the orbitals used in sigma bonds. Group theory can be used to predict which orbitals on a central atom can be mixed to create hybrid orbitals. Now, how to determine hybridization? First of all, determine the point group of the molecule. Then consider the sigma bonds as vectors and determine how they are transformed by the symmetry operations of the group. Then obtain the characters of the bonds. For each symmetry operation, a bond which remain in the place contributes a value of +1. If the bond is moved to another position, it contributes a value of 0. Now reduce the set of characters to a linear combination of characters sets of the point group, that is irreducible representation. That is the reducible representations obtained by the bonds as taken as a vector now converted into the irreducible representations. We will take the example of BF3. Determine the hybridization of boron in BF3. The molecule is trigonal, planar and belongs to the point group D3H. So consider the sigma bond as vectors. So these the 3 sigma bonds and these 3 sigma bonds considers as a vector A, B and C. Now determine the reducible representation of these 3 bonds by operating all the operations. So identity. In identity, all the 3 bonds remains at their place, so it will be the 3. C3 operation, all the 3 sigma bonds will move, so there will be 0. C2 operation, in C2 operations, 1 sigma bond, if by this bond we will rotate, the 1 bond will be at the same place and 2 bonds will be disturbed or moved, so it will be the 1. Sigma H, the plane of the molecule, in this the operation all the 3 sigma bonds are at the place, original place, so it is 3. In S3 it will be 0. Sigma V, it is the plane passing through this, then the 1 sigma bond is not moved and 2 are moved, so it is the 1. Now the reducible representation into the irreducible representation. This formula we have discussed in earlier lectures. So an I is equal to 1 upon H summation of C G C chi I chi R. An I is equal to the number of times an irreducible representation I occurs on the reducible representation. H, the order of the group, the total number of operations in the point group. C, the class type of operation. GC, the number of operation in the class. Chi I is equal to character of the irreducible representations. Chi R is equal to the character of the reducible representation. Now this is the formula by which we can determine the irreducible representations. So these are the reducible representations and these are the operations in D3H. This is the character table of D3H. So the order of the group H is the total number of operations H, that is 1, 2, 3 plus 1 plus 2 plus 3, that is equal to 12. So the order of this group is 12. If we reduce the reducible representations, then tau reduces to A1 dash plus E dash. The orbitals used in hybridization must have this symmetry. So the A1 dash and E dash, these two symmetry, these irreducible representations belong to the symmetry. Now in this character table we can find that A1 dash, the base will be x square plus y square and z square. So the s orbitals and the dz orbitals on boron have A1 dash symmetry. So this x square plus y square represents the s orbital and z square will be dz square orbitals. So in this A1 symmetry, these orbitals are used. The 3 dz square orbital is too high in energy to hybridize. So the dz square orbital will not take part in the hybridization. Now the E dash, the px and py orbitals and the dx square minus y square and dxy orbitals have E dash symmetry. So in E dash symmetry, this xy, so this is px py and this is dx square minus y square and dxy. Since the d orbitals on boron are too high in energy, they will not be used in the hybridization. Now, so we can conclude that the hybridization of boron will sp2, because this is the s and p2, or more specifically as px and py. Now we will discuss the hybridization in CH4 molecule. So this is the CH4 molecule. We obtain the reducible representation of CH4 molecule by applying the symmetry operations. So these are the symmetry operations in tetrahedral molecule E, 8C3, 3C2, 6S4 and 6 sigma D on 4 vectors sigma H bond, because there are 4 bonds, so we will take these 4 bonds as vectors. Now the reducible representation of the CH4 molecules are for identity operation. All the 4 bonds will remain at their position, so it will be the 4. In C3 position, this will be 1, C2 will be 0, S4 will be 0, sigma D will be 2. So these are the reducible representations of the 4 sigma bonds or 4 vectors. This reducible representation is split into the following irreducible representations. These reducible representations can be converted into the irreducible representation by the formula. So the irreducible representations will be A1 plus T2. The possible combination S of orbitals with A1 and T2 symmetry. So in A1 symmetry, This is x square plus y square plus z square. This represents the s orbital. And in T2 symmetry, this is x, y, z, that is px, py, pz, or these are the d orbitals, dx, y, dxz and dyz. The possible combination of s of the orbitals with A1 and T2 symmetry. So these are the irreducible representations, that is A1, T2. Coordinates or products of coordinates or binary product of coordinates will be x square plus y square plus z square. It is in the A1 symmetry. And in T2 symmetry, x, y, z, xy, xz and yz. So for this symmetry gives to the s orbital, this x, y, z will give you px, py and pz, and this is the dxy, dyz and dzx. Two possible types of hybridization with tetrahedral symmetry, that is sp3, either this s or this p3, s or p3, and sd3. Since carbon does not have d orbital, so sp3 hybridization on the 4 CH bonds, sigma bonds. So there will be the 4 sigma bonds will hybridize by the sp3 hybridization.